Swayam Prabha. Digital India. Educated India.
Lecture 2, TA 101, Think and Analyze. I always try to extract some sense from nonsense. So, you know what this word is. You guys are students, so you would be familiar with this word, cheating. And I'm a teacher, so I'm familiar with this word, teaching. Now, what is common between these two words, cheating and teaching? If you rearrange the alphabets over here, you would essentially get this. Do you know what this is called? So, these two are anagrams of each other. So if you're on the other side of the table, you would probably be indulging in this. While if you're on this side of the table, like me, I would be indulging in this. And my job is to have you guys not do this. Anyhow, polygons and conics. What would a polygon say to a conic? So, this is this, I'm a movie buff, and I was watching this movie, Jerry Maguire. And Jerry Maguire was managing one of the football players, one of the upcoming football players, and there are like two phrases in that movie which I like very much, which I guess you all may also be familiar with. Anyway, so what would a polygon say to a conic? Show me the bunny. In the movie, it's like show me the money, show me the bunny. Here you go. And what would or how would a conic retort? Draw me, draw you. Help me, help you. Draw me, draw you. All right. So, Tom Cruise, I'm sorry. But anyhow, so basic construction and conics. So, this is what I'm going to be covering in this lecture. So, this is the second lecture in the first week, Introduction, Basic Constructions. All right, so we will be focusing on how to construct a hexagon. It's in the family of, it's a member of the family of polygons. And there are these two methods that we'll be discussing, vertex to vertex distance method and distance between flats. All right, so given two vertices, this one, and let's say we are given this distance d between these two vertices. How do I construct a hexagon? So this is what I would do. I would divide this line into two equal parts. I'll draw an arc with this as center and radius as d over 2, and another arc with this as center and radius as d over 2. Okay, so that these two arcs, they happen to meet at the midpoint of the line and are also tangent to each other. And with this midpoint as center, I'll draw a full circle of radius d over 2. Essentially, this circle is going to be traversing through the endpoints of the edge. Okay, so focus on this intersection point, this one, and this one. So, and these two in addition. Okay, so 6 points, they'll essentially form the vertices of the hexagon. All right, so if you look at this circle and the hexagon, so this circle happens to be the circumscribing circle of the hexagon. Second method, distance between flats. So this is the first flat over here, this is the second flat over here. This distance d is given to us. How do we draw a hexagon? I'll mark the midpoint of this line segment, draw a circle of radius d over 2 with this midpoint as center. I'll draw a horizontal line, and then I'll draw a line which is tangent to the circle, and this line is such that it is making an angle of 60 degrees with the horizontal. I will draw another line which is parallel to this line and tangent to this circle. Okay. And then I will draw a horizontal line tangent to the circle at the top. I will extend this horizontal line below, again tangent to the circle at the bottom. And then I will draw this line which is at 120 degrees to the horizontal and a line parallel to this line. All right. So, this point over here, this point, this point, this point, this point, and the sixth point here, they essentially form the vertices of a hexagon. So, you can actually join these vertices and eventually construct a hexagon. So, the way this construction is done, the circle happens to be the inscribing circle inscribed within the hexagon. Vertex to vertex distance, distance between flats. In this case, the parent circle or the main circle happens to be the circumscribing circle. In this case, the parent and the main circle happens to be the inscribing circle to the hexagon. All right. Now, this is something very interesting. How do you draw a pentagon? So, given a line segment whose endpoints are at distance d. Okay, so, the endpoints are marked as A and C. So, with the midpoint of AC line segment as center, we draw a circle with radius d over 2. Okay. And then what we do is we bisect this line segment BC. Okay. We draw a vertical passing through B, intersecting the circle at D. So, once we bisect this line segment BC, we will get a point over here. Let us mark it E. Now, notice that we are going to be working with distance DE. Let us say this is of magnitude R. Now, with this distance and with ES center, we are going to be drawing an arc which is going to be cutting the line segment AC at F. Now, this length over here, let us say this is capital R. With this radius capital R and with let us say point D as center, we will cut the main circle at this arc or at this point. Okay. So, this length over here from here to here is capital R. Okay. Now, with this as center and the same radius, we will cut the main circle again at this point and we will continue doing so until we get 5 points on the circumference 1, 2, 3, 4 and 5. These 5 points will constitute or will be the vertices of the pentagon we are seeking. Now, think and analyze. How is it that you think that this is a pentagon? Is it difficult for you to appreciate or perhaps not? Let us try to prove that this is really a pentagon. Let me grab a piece of chalk and let me focus on this region over here. So, this is my point B. Here is my point D. DB is half of the diameter of the circle. So, it is D over 2. Now, this distance is again D over 2 and BE is half of BC. So, BE would be D over 4. And now, look at this distance dE. Let's first try to figure what this distance is. So this is r, then we'll have r squared by Pythagoras theorem as d squared over 4 plus d squared over 16. This is equal to, if I multiply and divide by 4 here, 5 d squared over 16, implying that r is d over 4 times root of 5. All right. Now let's try to figure what this distance is, capital R. Now if I go leftward from B, I'm looking at point F here. Okay. Now by construction, so with this point E as center, what I had done was I had cut the diameter AC with the arc of radius r. So this distance here would also be r. Okay, and therefore if B will be r minus BE, which is d over 4. So if B is r minus d over 4. And so this capital R here, dF, can also be determined using Pythagoras theorem. So capital R squared equals d squared over 4 plus the square root of this, r minus d over 4 the whole square. Now let's retain this thing in the squared form because we'll be needing that. Now focus on the triangle. Well, let's call this point M, MBD. Okay. Now this distance MD is the same as capital R. This distance is d over 2, the radius of the circle, and this distance is again d over 2, the radius of the circle. So let me draw this point here somewhere, M. So this distance here is capital R, this is d over 2, and MB would again be d over 2. And let me say now that I am interested in trying to find what this angle theta is. So we can use the cosine rule, and the cosine rule is such that cosine of theta equals d squared over 4 plus d squared over 4 minus this distance over here, r squared, over 2 times d over 2 d over 2, which is equal to, this is d square over 2 minus r squared over, this is again d square over 2, which is 1 minus 2r squared over d squared. I hope I am doing this right. I can substitute this value over here. So cosine of theta, let me write this thing down here, equals 1 minus 2 times r squared is d squared over 4 plus small r minus d over 4 the whole squared over d squared. Okay. which is equal to 1 minus, within parenthesis, this would be 1 over 2, yeah, minus 2 over d squared r minus d over 4 the whole square. Let's substitute this value over here and let's see what we get. This is equal to, well, half plus 2 over d squared and this is d over 4 root of 5 minus d over 4 the whole squared, right? Okay. And so this would be equal to half plus 2. So this d would come out and get cancelled with d squared here. From here we will be getting 16. So let me write this thing down over here, 16, and then this is root of 5 minus 1 the whole square. Let's see what this is. Well, let me erase this and take this thing up over there. So this is half plus 1 over 8, and this is 5 plus 1, 6 minus 2 root of 5. Seems a little awkward. Let's see where it takes me. Half plus 3 over 4 minus root of 5 by 4. Okay. This is equal to, if I multiply and divide by 2, I've got 5 over 4 minus of root 5 by 4. So I just realized that I made a mistake here. I make a lot of mistakes. So instead of the positive sign over here, I should have really had a negative sign. So I'll go back and correct my mistakes. So this is a negative sign here, because of which this would be negative, because of which I guess this would be negative, and this would be positive, and so this actually would be equal to, 2 minus 3 over 4 plus under root of 5 over 4, which is root of 5 minus 1 over 4. And if you go back and try to figure what cosine of 72 degrees is, then you would see that this is nothing but this value here. So in a sense, through geometric construction, what we do is we essentially divide the circle into 5 equal parts in such a way, ensuring that this angle here, theta, is equal to 72 degrees, this angle. So once we ensure this, it becomes a little easier for us to construct a pentagon, again through geometry. So this was an algebra, this was the algebra just to support the construction of pentagon, but you would have realized that we did not actually need this algebra in construction of the pentagon. Anyway, so let's move forward. So these 5 vertices, they'll essentially be a part of this pentagon. How would you construct an octagon? All right. So let's say you have a square of equal dimension sides. All right. Draw 2 diagonals. indicate these vertices from this as center and this length as the radius, draw an arc. Okay, do the same with this as center and the same radius. Again, the same radius with this as center, and finally with this as radius, with this as center and the same radius. So draw these bunch of arcs, and wherever these arcs are going to be intersecting the edges. So here, 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 and here, you'll essentially have 8 vertices. Join them, and you will be getting an octagon. It's a pretty simple construction. I think can analyze, through algebra or otherwise, if this is really an octagon or not. Okay, how about a regular septagon or any other regular polygon for that matter? Given a side, so let's say you have given a side, you have been given a side. All right, so you have this point over here, this distance is known. So draw a semicircle and divide this semicircle into, so since we are focusing on septagon, so divide this semicircle into, let's say, 1, 2, 3, 4, 5, 6, and 7 equal parts. And name them in such a way that you let go of this first point on the left. So start naming them as 2, 3, 4, 5, 6, and 7. Right? And then draw. Oh, well, this happens to be the center of this semicircle over here. Name that center as A, and one of the ends of the semicircle as B. Now draw radial lines in such a way that they happen to be connecting this point A here and all these points on the semicircle. So once you're done with that, take this as your distance, your reference distance. Mark that on your compass with point 7 as center. Mark an arc on this edge with this point as center. With the same radius, mark a point on this line segment. With this as center, same radius, mark a point over here, and keep going forth. Okay, until you mark a point over here. Okay, and then once you have gotten all these points, vertex 1, 2, 3, 4, 5, 6, and 7. So these are the 7 vertices that will essentially constitute your septagon. So this is a generic method that allows you to draw any regular polygon. Construction of an ellipse by means of concentric circles. So you got this larger circle, you got this smaller circle, they happen to be concentric, same center. Divide both circles into equal number of parts. So I believe I would have divided the outer circle as, or into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 equal number of parts, and likewise the inner circle also into 16 equal parts. Now this is what the trick is. From one of these points, draw horizontal. From one of these points, corresponding points, draw vertical, or vice versa. Let's see. So I draw horizontal from the inner circle and vertical from the outer circle. Okay, corresponding points. Over here, horizontal, vertical, horizontal, vertical. Okay, horizontal, vertical, horizontal from the inner, vertical from the outer. Horizontal, vertical, horizontal, vertical, horizontal. Okay, and these points, they essentially will be lying on an ellipse. All right, I could do the other way around. For example, instead of drawing the horizontal from the inner circle, I would be drawing the horizontal from the outer circle. Well, this is the construction of the ellipse for the first case. As I said, I'll be drawing the horizontal from the outer circle and vertical from the inner circle this time. All right, so horizontal, vertical, vertical, horizontal, vertical, vertical, horizontal, vertical, horizontal, vertical, horizontal, and thus I'll essentially be getting these points, and they will happen to lie on an ellipse, which essentially will be oriented 90 degrees. So these are the points on the ellipse, and I'll join these points and get another ellipse. Now the question, think and analyze for you is this or this an exact ellipse or not? Let's try to find it out. So let's join the corresponding points on the inner and outer circle. Have this horizontal, have this line segment over here, let this angle be theta. So let this point P, or rather let this point be P, and the coordinates of P would be B cosine of theta and B sin of theta, where B is the center of, or B is the radius of the inner circle. Likewise, point over here Q will have coordinates A cosine of theta, A sin of theta, where A is the radius of the outer circle. Okay, and if you focus on this point, okay, what would be the x coordinate of this point and what would be the y coordinate of this point? Can you guess? You have these values over here. So the x coordinate of this point essentially will be the x coordinate of Q, and the y coordinate of this point would be the y coordinate or the ordinate of P. So essentially, if this point is represented as x and y, then x will be A cosine of theta, y will be B sin of theta. And of course, if you go back to your 11th grade or 12th grade coordinate geometry, you would readily confirm that x, y is nothing but a point on the ellipse, and therefore this ellipse is an exact ellipse. Yeah. All right. So if I want to draw a tangent or a normal at any point on the ellipse, what do I do? Let's say I have this point here. I would like to draw a tangent or a normal at this point, P. Okay. Now what I'll be doing is I'll be using one of the properties of the ellipse. First, I'll try to figure the focal, or the two foci. Now let me go back. Let me draw the horizontal, and let me also draw the vertical. I'll sit at this point, let's say, and I would rather already know the length of the major axis of the ellipse. Okay, I'll take half of that distance. With this as center, I'll draw two arcs over here and here. This point being M. Okay, I'll mark a point over here. So this distance is half the major axis, and I'll also mark a point on the other side of the major axis. So these two circles would represent the two foci of the ellipse, and the property I'm using is straightforward. So if I take any point on the ellipse, okay, so the distance of this point from this center and this center, if I sum these two distances, that sum will always be equal to the length of the major axis. So two foci F and G, and this is the property I just had mentioned. So M being a point on the ellipse, distance Fm plus distance Mg has to be equal to 2a, where a is the length of the semi major axis. Okay, so having found the two foci, I'll join, or I'll draw a line segment joining F and P. I'll draw another line segment joining P and G. I'll take the angular bisector of the angle FPG. You know how to draw the angular bisector. And this line over here essentially will be the normal at point P. All I need to do is, using a compass or using a ruler, I have to bisect this angle. This angle is 180 degrees. I have to bisect it, and I'll do exactly the same thing, bisect the angle. once I do that, this line segment here will be the tangent to the ellipse. Normal to the ellipse n and tangent to the ellipse. Now think and analyze TA. Why is the n, this line segment normal to the ellipse? Okay, construction of ellipse by intersecting arcs. Again, I'll use the same property I had discussed before. So if I have a point M on the ellipse, and if I have these two foci of the ellipse, well, these are not the foci, but they happen to be the points at the extreme ends of the semi or of the major axis. Okay, so if the length of the major axis is 2a, if the length of the minor axis is 2b, it should be this way, I guess. Never mind. So the property is any point, well, let me see. If f and g are two foci, and if t is any point on the ellipse, then ft plus tg has to be equal to 2a. All right. So what I'll do is I'll divide 2a into equal number of parts. Let's say the entire length, this length over here, which is given to me, into equal number of parts. Let me mark the extreme points on the ellipse as P and Q. Okay. There I go. Well, and then what I would do is, if I choose, let's say, this length, okay, and draw an arc with center F and this length, then I'll have to choose this length for the radius of the other arc that I'm going to be drawing with G as center. That would be my point, one of my points T on the ellipse. Okay, and I'll do that, for as many points as possible. Once again, so if I choose, any other point over here, let's say this one, if I choose this length with this length as radius and this as center, I'll draw another arc, and with this as the radius and center as G, I'll draw the second arc. The intersection of these two arcs will give me another point. So I'll keep getting these points, and that would essentially help me draw the ellipse. Straightforward. Think and analyze what is the maximum radius of the arcs possible from point F or G. That's for you to think. Always a good idea to think. Okay, let's do a little bit of algebra. Choose any point T over here. Let's mark Ft as distance d1, and let's mark Gt as distance d2. Let the coordinates of T be x and y, and it so happens that point T is a result of this property that d1 plus d2 has to be equal to the length of the major axis of the ellipse, 2L. Okay, and essentially d1 plus d2 is a constant because 2L is constant for a given ellipse. Now, for a simple case, if I choose G such that it has coordinates a0, then F would be such that it would have coordinates minus a0 with this point as center. And if I do a little bit of algebra, so d1 essentially would be, x plus a the whole squared plus y squared, and d2 will essentially be x minus a the whole squared plus y squared, and that's equal to constant. And with a little bit of algebra, I'll get this equation: x squared over c squared over 4 plus y squared over c squared minus 4a squared, the entire thing over 4 is equal to 1. And it so happens that if you choose if you represent this as some a1, if you represent this as some b1, then it's like x squared over a1 squared plus y squared over b1 squared is equal to 1, which is the equation of an ellipse. So apparently this happens to be an exact ellipse, and precisely so if this constant c is greater than or equal to 2 times a, I think. Yeah. All right, so you can use the same property. Let me go back. You can use the same property, have a pin here at one of the foci, have another pin here at the second focus, and you can have a loop of string. So this distance and this distance, making sure that the sum of these two distances is a constant, you can draw an ellipse. Trammel of Archimedes, another way of constructing an ellipse. All right. So let's say you have 2 line segments, M and N. Well, so you have this length equals 2a. Have 2 points, red and green. Okay, and have this entire ruler placed on the vertical with the same 2 points, red and green. And start moving this ruler in such a way that the green is always on the horizontal and the red is always on the vertical. Okay, and let me go back. See what's happening. Focus on this point. Green always on the horizontal, red always on the vertical. This point is actually leaving some traces out over here, and these traces are nothing but points which are going to be lying on the ellipse. So you can do the algebra and figure that this also kind of gives an exact ellipse. Let me skip this algebra. Well, let me go back and let me try to work out the algebra for you. All right, so for any position of this line, you'll have this as distance y, you'll have this as distance x. Okay. Join point R with the vertical over here. So this triangle and this larger triangle, they are essentially similar triangles. Let me call this y1, let me call this x1, and let me have this length as L1 and this length as some factor f of L1. Because the triangles are similar, it should be possible for you to work out the ratio. X1 over x is the same as 1 over 1 plus f, y1 over y is the same as f, and x squared plus y squared is equal to L1 squared. Do a bit of algebra and you will get x1 over 1 plus f the whole square plus y1 over f the whole square equals L1 square. Precise ellipse. I make a lot of mistakes, so don't trust me. Work this algebra out by yourself. You'll realize that I may have made a mistake. Construction of ellipse, the parallelogram method. Given a parallelogram, how do you construct an ellipse? How do you construct an ellipse? Well, divide this parallelogram into a bunch of parts at the top. I guess 8 parts here, like so. And also, well, but before that, mark these points. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and also divide this side of the parallelogram into those many equal number of parts. Now watch out for the way I am numbering them. I am numbering these points from here, 0, 1, 2, 3, 4, 5, 6, 7, 8, and over here is going to be slightly different. is going to be from here to here. Okay. So, once I have that, then I will have one reference point over here and the other reference point over there, and watch out for the line segments I am constructing. Well, in fact, I can have the same points on this side. Watch out for the line segments I am constructing. So, I would imagine that this point and this point essentially will be lying on the ellipse. With this as reference, I will have my line segment pass through point 1. With this as reference, I will have my line segment pass through point 1. This is a point on the ellipse, the intersection of this line segment and this line segment. Okay. From here, I will have a line segment pass through this point 2, and from here, I will have my line segment pass through this point 2 here. So, the intersection of this line segment and this line segment over here will give me another point on the ellipse. So, it is always a good idea for you to have some reference associated with the points or the geometric entities that you are using for construction. For example, from here I will draw a line segment passing through 3. From here I am going to be having a line segment passing through this point 3 here. Intersection of these two line segments will be a point on the ellipse, and I will continue like so. Okay. All right. I can do the same thing on this side of the parallelogram. Won't say a word, just follow the construction. Okay. And what I could do is I could mirror these sets of points over there, mirror this set of points over here, and once I have these points, essentially all these points, they happen to be lying on the ellipse. All right. Okay. Now you try to figure if this is an exact or an approximate ellipse. Also, is it possible for you to identify the conjugate diameters? Try to figure it out. Construction of ellipse, another method by means of conjugate diameters. So, given two conjugate diameters, let me name them as AB and CD. They intersect at point O. AB and CD are conjugate diameters. Let us say O is the center of the ellipse. Now, with O as the center and AB as the diameter, I am going to be drawing this outer circle in red. And let me draw OQ such that OQ is perpendicular to AB. Let me join point D and Q. Let me divide this outer circle into, say, equal number of parts. Let me also join point C with the end point over here. Now, you would see that I am using line segments with different colors just to indicate that they are parallel. So, this line segment is parallel with this line segment. Now, watch out what I am going to be doing with these points. Be careful. Now, I am going to be drawing a line which is parallel to this line here, OQ, and likewise over here. Again, I am depicting these lines using color blue just to emphasize that these lines are parallel. Now, from here I am going to be drawing a line parallel to CD, and with one of the points over here I am going to be drawing a line segment parallel to DQ, and likewise from here as well I am going to be lying, rather I am going to be drawing a line segment, I am not lying, I am going to be drawing a line segment parallel to DQ from here. So, of course, this point and this point theoretically will be a part of the ellipse. Likewise, I will draw a line segment parallel to CD such that it passes through the intersection between this blue line and the line AB. From here I will draw a line parallel to OD. From here I will draw a line parallel to again OD, and of course this red line over here, they would be intersecting with the purple line. So, these 2 points again will be belonging to the ellipse that I am seeking. Okay, so, once again point here, here, intersection between the purples and the reds will essentially give me points on the ellipse, intersection between the purples and reds. So, this is how I draw an ellipse using conjugate diameters. Is this an exact ellipse? Go figure. All right, one of the final methods of constructing an ellipse, the 4 center method. So, given a rhombus, once again given a rhombus, these 4 lengths are the same, just that the angles are not 90 degrees, otherwise it would have been a square. Identify the centers of each of the line segments. Okay. Now, the first thing you would want to do is identify and draw the longest diagonal. So, of course, this one is not the longest diagonal, but the other one which is the longest diagonal. Now, look at this point, go to the opposite vertex, join this point with this vertex, and likewise look at this point, look at the opposite vertex, join this point with this vertex. So, you will essentially have this as one of the centers, this as one of the centers, and 2 more centers. So, let me call this center as C1, with C1 as center and this as radius, draw an arc. So, of course, this arc is going to be having these 2 points lying on it, with this point as center and this as radius, draw another arc that will be having these 2 midpoints of the respective edges of the rhombus on it. The 3rd center, or rather the 4th center, would be here, the 3rd center would be here. Okay. So, with this as center, this as radius, draw the 3rd arc, and with C3 as center and this as radius, draw the 4th arc. Looks like an ellipse, but is this an exact ellipse? I will give you a clue. Well, if you think about this, this is actually an arc. Think about this, this also is an arc, rather, or likewise these 2 are also arcs. So, of course, I mean this cannot be an exact ellipse, it has to be approximate. Again, so to be able to construct an ellipse using the 4 center method, step 1, identify the longest diagonal. Okay. But before that, make sure you locate the midpoints of the 4 sides of the rhombus. Okay. Now, there would be a vertex on this side of the longest diagonal and on this side of the longest diagonal. So, one vertex over here, one vertex over here. Identify those vertices and join the corresponding vertices with the corresponding midpoints of the edges of the rhombus. So, from here to here and then from here to here. Okay, so, you will essentially have 4 centers, center C1, center C2, center C3 and center C4, and follow the procedure As I said, this has to be an approximate ellipse because all these 4 geometric entities are arcs. They cannot be a part of the ellipse. And of course, this, as I said, the clue, you have to identify the longest diagonal first. But this method works only with rhombus. It doesn't work with parallelograms, for example. So for example, if this length and this length, they have to be the same, and if they are different from these 2 lengths, then this method will not work. Incidentally, this arc has to be tangent to these 2 line segments. This part, it has to be tangent to these 2 line segments. And that would not be the case for any generic parallelogram. Construction of a parabola. All right, so given one line segment, divide that into equal number of parts. Let's say 1, 2, 3, 4, 5, 6, 7. Another line segment, divide them also into equal number of parts. Just make sure that you follow the numbering. So for this line segment, I'm now numbering from this point over here, which is the intersection between this line segment and this line segment. For the other line segment, I'm numbering the other way around. So I'm starting from one of the endpoints of this line segment. And join 1 to 1, 2 to 2, 3 to 3, keep going. Okay, and try to figure an arc that is tangent to all these line segments. Okay, once you get that, so it's this green curve which is the parabola that you're seeking. Keep thinking and analyzing. Until next time.